Hello everyone, I'm Vikram Madduri here. I'm a software architect and welcome to Softech. In this session, we're going to discuss about certain topics on in chapter 1 of machine learning, part 5. This was the part 5 session. In this, we're going to discuss more about marginalization, independence, conditioning, and base rule. So we have started off with the introduction of marginalization, independence, conditioning, and base rule. We are going to discuss in detail more about these concepts with certain examples. So let's consider a couple of examples and understand this concept furthermore so that we can get a basic clarity of the machine learning. So here in this series of sessions that I'm taking up in machine learning, I'm trying to simplify the concept as much as possible in and let us all understand it from the day-to-day activities. I'm giving it certain examples from our day-to-day life, and then we can easily connect that to the machine learning concept. Now let's take an example of we have example of AIDS test. So let's say we need to test couple of people across a unit of people in which we had to test whether they are AIDS positive or negative, HIV positive or negative patients. So we need to carry out the test, and we have to finalize whether a person is HIV positive or HIV negative. So let's take this AIDS test example in which if we have healthy patients, there might be a chance that 1% error rate might be there, wherein even if the person is HIV negative, it might show that that particular person is HIV positive, and the percentage of that population which is actually the error rate is 1%. So if at all, if you check 100 people for the HIV test, there might be one person who is actually HIV negative, but he might be shown as HIV positive. So that's the probability that we're taking here. And that is the probability zero point zero 0.01. It diagnoses a patient as HIV positive, even when it is in fact HIV negative. Moreover, assume that 0.15 of the population is infected. Now, 0.15 in the sense like it'll be like if we take into consideration say 1,000 people, in 1,000 we have 15 people who are infected with HIV. So now assume that the patient has the test carried out and the rest test returns HIV negative. In this case, logic implies that he is healthy since the test has 100% detection rate. So in converse case, things are not quite as straightforward. Now denote by X and T the random variables associated with the health status of the patient and the outcome of the test respectively. So we are interested in probability of P of X is equals to HIV positive or T is equals to HIV positive. Now by base rule, we may write that P of X is equals to HIV positive or T is equals to HIV positive is equals to P of T is equals to HIV positive, X is equals to HIV positive of P of X is equals to HIV positive slash P of T is equals to HIV positive. So what I would recommend you is to go back and check and write down the base rule. When we compare this with the base rule, you'll be getting more clarity on what exactly we are talking about here. So while we know all terms in the numerator, P of T is equals to HIV positive itself is unknown. So that said, it can be compounded via P of T is equals to HIV positive is equal to X. X belongs to HIV positive, HIV negative. P of T is equals to HIV positive. X is equals to X. X belongs to HIV positive, HIV negative. So P of T is equals to HIV positive of X, P of X. So this is equal to 1.0 into 0.0015 plus 0.01 into 0.0015 0.9985. Now substituting back into the conditional expression yields to probability of P of X is equals to HIV positive or T is equals to HIV positive would be equal to 1.0 into 0.0015 by 1.0 into 0.0015 plus 0.01 into 0.9985. That would equal to 0.1306. So when we calculate the entire calculation here, this entire thing that we have done, the final output would be 0.1306. It means that P of X is equals to HIV positive or T is equals to HIV positive is equal to 0.1306. That's what it means. That's what it means. Now, in other words, even though our test is quite reliable, there is such a low prior probability of having been infected with AIDS that there is not much evidence to accept the hypothesis even after this test. Now, we'll take a graphical representation of age. So, in this, we have a graphical representation of HIV test scenario. Knowing the age of the patient influences our prior on whether the patient is HIV positive. The random variable X, the outcomes of the test 1 and test 2 are independent of each other given the status X. So, we observe the shades random variables, for example, age test 1 and test 2, and would like to infer the unshaded random variable X. Now, this is special case of a graphical model which we will discuss in the chapter next coming chapters. So in this we have test 1 and test 2. If at all in test 1 and test 2 if the results are same, the probability of we can conclude that the test is fine. I mean it's right, correct. So this is what we have. So let's say test 1 says that particular person is HIV positive, and test 2 also says that he is HIV positive, then there might be high possibility, probability of that person being HIV positive. Now let us now think how we could improve the diagnosis. So one way is to obtain further information about the patient and to use this diagnosis. For instance, information about his age is quite useful. Suppose the patient is 35 years old. In this case, we would want to compute P of X is equals to HIV positive, T is equals to HIV positive, A is equals to 35, that's the age, where the random variable A denotes the age. So the corresponding expression yields P of T is equals to HIV positive, X is equals to HIV positive, and A, and probability of X is equals to HIV positive and of A, and P of T is equals to HIV positive and A. Here we simply condition all random variables on A in order to take additional information into this account. So we may assume that the test is independent of the age of the patient. So it means that P of T X comma A is equals to P of T by X. What remains therefore is P of X is equals to HIV positive of A. Recent US census data pegs this number at approximately 0.9%. So plugging all data back into the conditional expression yields 1.0, 1 into 0.009, 1.0, 1 into 0.009 plus 0.01 into 0.991, that would come to 0.48. So what has happened here is that by including additional observed random variables, our estimate has become more reliable. The combination of evidence is a powerful tool. In our case, it helped us make the classification problem of whether the patient is HIV negative or HIV positive. And in case like we are trying to get more reliable information. A second tool in our arsenal is the use of multiple measurements. So after the first test, the physician is likely to carry out a second test to confirm the diagnosis. So we denote by T1 and T2 and T1, T2 respectively, the two tests. Obviously, what we want is that T2 will give us an independent second opinion of the situation. So in other words, we want to ensure that the T2 does not make the same mistakes as T1. For instance, it is probably a bad idea to repeat T1 without changes, since it might perform the same diagnostic mistakes as before. So what we want is that the diagnosis of T2 is independent of that of T1, given the health status of X of the patient. So this is expressed as ASP of T1 T2 of X is equals to probability of T1 of X P or probability of T2 of X into 1.16. So if we see the coming figure, so we'll be discussing about the figure, so wherein like for a graphical illustration of the settings, the random variables satisfying the condition 1.16 are commonly referred to as conditionally independent. So in shorthand, we write T1 and T2 of X for the sake of argument. We assume that the statistics for T2 are given by probability of T2 of X is into X is equals to HIV negative of X is equals to HIV positive by T2 is equals to HIV minus the X value, that is 0.9595 into 0.01. So that would be T2 is equals to HIV positive 0.05, 0.99. Now, clearly this test is less reliable than the first one. However, we may now combine both estimates to obtain a very reliable estimate because based on the combination of both events. So for instance, for T1 is equals to T2 is equals to HIV positive, we have P of X is equals to HIV positive, T1 is equals to HIV positive, T2 is equals to HIV positive. So is equals to 1.0 into 0.99 into 0.009 by 1.0 into 0.99 into 0.009 plus 0.01 into 0.05 into 0.991 is equals to 0.95. Now, when we calculate, the final thing would be is equal to 0.995. Now, in other words, by combining two tests, we can now confirm with very high confidence the patient is indeed diseased. If at all, if he is HIV positive. So in both the cases, both the independent cases of T1 and T2, if it is been confirmed that the patient is indeed HIV positive, then there is a high probability that he is indeed a HIV positive person. So what we have carried out is a combination of evidence. So strong experimental evidence of two positive tests effectively overcame an initially very strong prior which suggested that the patient might be healthy. Now, tests such as in this example we just discussed are fairly common. So for instance, we might need to decide which manufacturing procedure is preferable, which choice of parameters will be given better results in a regression estimator, or whether to administer a certain drug. So note that often our tests may not be conditionally independent, and we would need to take this into account in certain situations. Not all, in certain situations, we have to take the previous test into consideration. Now, the basic algorithms is what we have here. We will be discussing about the basic algorithms in the coming session. So this is something which we have discussed about one example which we have taken on HIV positive and HIV negative a scenario. In the session 6, I'll be discussing about the basic algorithms. So thanks for watching this video. If you do like this, click on the like button, share it with your friends. It might help them as well. And do subscribe to our channel, and do not forget to click on the bell button when you subscribe. You can subscribe to us at www.youtube.com/jsoftech. And do let me know your comments, and I'd be taking it in your comments are most important for me to improve.